Every machine has built-in safety parameters. The universe operates by the same logic, enforcing a maximum speed, a lowest possible temperature, and an absolute limit on how massive a single object can become. TON 618 is the exception to those rules. When astronomers first cataloged it in 1957, they mistook it for a faint blue star within our own galaxy. The instrumentation of the era could not register the true distance, leaving its actual nature hidden for decades. To understand TON 618, we have to look past the star charts. We are analyzing a point where the governing systems of the universe have reached a state of critical instability. TON 618 registers at 66 billion times the mass of our Sun. Consider the scale of our own solar system. The distance from the Sun to the furthest orbit of Neptune spans 9 billion kilometers, an expanse of almost entirely empty space. Map that entire planetary system against TON 618, and our neighborhood shrinks to a speck. The boundary spans 390 billion kilometers. That glowing edge is the Schwarzschild radius, the precise boundary where the mathematics of space and time divide by zero. This magnitude creates a profound problem. Based on the established timeline of the cosmos, TON 618 physically lacked the space and the time required to grow this large. The void is only part of the mechanism. Most of the mechanical violence happens right outside the perimeter, in the fuel system powering it. TON 618 is a quasar. As gas and stellar material fall inward, the intense rotation flattens the debris into a superheated accretion disk, spinning much like molten metal in a centrifuge. Gravity alone generates this blinding white light. As matter spirals in, gravitational friction tears atoms apart at the subatomic level, releasing pure radiation. The resulting thermal output is staggering. The friction generates the brilliance of 140 trillion suns. Radiation this intense sterilizes the surrounding environment. It strips away the gas clouds needed to form new stars, creating a dead zone that spans the host galaxy. This is a violently active industrial system, the most powerful engine in the known universe. Operating an engine of that power involves a severe mechanical conflict, the tug-of-war between gravity pulling matter inward and radiation pressure pushing it outward. This dynamic is governed by a safety protocol, the Eddington limit. It's a theoretical threshold where gravity's inward pull and radiation's outward push are balanced. If matter is consumed too quickly, radiation pressure surges, blowing incoming fuel away and choking off its growth. Yet TON 618 reached 66 billion solar masses, meaning it mathematically bypassed this universal protocol. Had it grown by steadily consuming surrounding stars according to the Eddington limit, the universe is not old enough for it to exist. Researchers point to the direct collapse theory. Instead of forming from a dying star, a dense cloud of primordial gas likely caved in on itself instantly, skipping standard stellar evolution entirely. TON 618 demonstrates that under the extreme conditions of the early cosmos, even the universe's foundational safety protocols have a failure point. This forces us to ask what happens to the billions of stars worth of material that cross that threshold. Under the holographic principle, information cannot be destroyed. Instead, the physical properties of everything swallowed are encoded as two-dimensional data on the surface of the event horizon. As we move through this data stream, consider the density. The surface area functions as a digital hard drive operating at maximum quantum efficiency. It acts as a physical archive, holding the complete structural data of a dead galaxy. While the universe achieved this data density on a scale of billions of kilometers, human engineers are currently attempting to navigate the same physical boundaries at the opposite end of the spectrum. You can see that struggle in this silicon wafer. We are pushing against the atomic limits of material science, attempting to etch circuitry onto chips approaching 1 nanometer scales. Both challenges are defined by the same constraint, the absolute limits of physical law. Whether we are measuring an event horizon or a nanometer of silicon, the real engineering begins where the standard math starts to break.